Okay, so hi everyone, my name is Andy, and I'm gonna show you how I try to optimize what I call ecosystem biodiversity, but it's a big word for so automating obviously using reinforcement learning. I'm not a reinforcement learning expert, but I wanted to learn. That's why I made this project basically. So you may actually know more about reinforcement learning than me at some point. But my motivation was that when I've seen all these beautiful images and all the applications that you could do with life, it felt a bit qualitative. Like it's very beautiful. You can maybe show some creatures, some patterns, etc. But it's hard to quantify what they actually are. And I thought that if ever you're a biologist, you have two types of approaches. Either you look at your system and you try to make your model look like your system one by one. You try to design the rules one by one. So you create a life system and you design the rules so that the system has to be. And the other way to do that is a top-down approach, where you know what your system looks like, and then you train the model in order to make the system learn what the rules should be, so that your model looks like your system. And eventually, it will have at the end similar behavior and interpretable parameters that you can then study. So there's two things. There's you can look at your system into the local scale. You can see that you have different particles that have different shapes, size, dynamics, and interactions. And you can also see it as a global scale. So your whole system, how many creatures you have, how many types of creatures you have, what are basically the evolution of these interactions. And I was more focused on the second part. So let's say if you take a look at the global scale, what would optimize basically the diversity of your system and while keeping it stable. So sort of thing. So what I did, I took the 2D cellular automaton that you all know about, and then I extracted some characteristics from the whole environment, which I then transferred into a reward function that will train a RL agent that will then try to optimize the S and B rule so that you have maybe more biodiversity. So yeah, I took the. There we go. So I started with the normal one, the game of life, rule B37 S23 with kernel size with 8 neighbors, the basic one. That's my environment. It looks basically like this. And I first tried to extract basically creatures from there, because you can see a lot of things happening. Sometimes it looks like noise. But what I was thinking is that you have some things that are almost stable. You have creatures that have the same shape all over the place, maybe have different orientations, but I think you have a limited amount of patterns that appears in the system. So I first made a pipeline to basically grid search everything on the environment. And for each grid, what I do is that I check if the borders are empty, if the inside is filled, and then you find a creature. And then I realign them. So if they have different orientation, I do PCA projection, and then you get so all these elements would basically refer to the same creature, and I basically create an encyclopedia of creatures that I found in my environment over time. And for this, I use 3 frames so that it's also a bit dynamic. Creatures can average over time. And some of them are very geometrical, like you have also the plus shapes or like very simple ones. And then some of them are a bit more complex, but I think might also be more transitional. They can appear only for 3 frames, for 4 frames, just because they are part of an interaction. But that's again something you can improve with a better detector, etc. That wasn't my goal. I just wanted to have something to start with. And those are basically all the elements now you have to create a good reward function. So yeah, again, after that I track them also, so that I don't lose track of them. So I know which creature is where. I track them in time, and basically I take the overlap of each track to renew them. So also take into account how long a creature survives, basically. That's hard to see also when you just see a system. Where it's hard to determine if a creature is self-reproducing, if it's surviving for a long time, if it's another creature that looks the same. So I think all those type of characteristics should be kind of quantified in when we do a model that is maybe relevant for a biological system. So then you can do a lot of stats. You can count the number of creatures you have per frame. You can count the size of your encyclopedia, so the variety of creatures that you have in your system. And then I create this table, which is kind of the diversity per frame. So this is the encyclopedia basically per frame. And you see that there's creatures that comes back sometimes, creatures that appears only very late in the scenario. So this is all the game of life. Okay, great. So now we have all this data, all these rewards elements that I want to fit it into a reinforcement learning agent. So reinforcement learning, for those who don't know, is basically composed of an environment and an agent that is trying to maximize a reward based on state by doing certain actions, and was found to be able to accomplish very difficult tasks like motion spinning. This is NVIDIA showing off their GPUs. When I read the code for the CA2, I thought that looks like a reinforcement learning code. There's a lot of things that are similar to step organization and class organization. I was like, maybe this was meant for a reinforcement learning application. So I used the PP algorithm, which is the default algorithm in OpenAI, which thought to be simple to implement. And basically it uses two things, the policy gradient methods and the clip R theta, which, let's say, it's doing a trade-off between doing an exploration that is trying to trade off the step size. So if you have a very large step size, then you have basically an exploration that's going to give you very high penalties. If you have, then you would maybe go for a very small step size and stay in your confidence zone, but then it's going to take a very long time in order to reach your goal. So it's trying to do this trade-off between optimizing this step size by having an in-between that is fast enough and also doesn't give you too much penalty. And finally, you have this clip R theta that basically says that your policy, so the types of steps you go, right, left, is updated not randomly. So you first try a policy, then you do a small variation of your first guess of policy. And if you do a too wide variation, you have a penalty in the algorithm, so that you only do small variations from the point from your initial guess, basically. And then I use the rewards being the creature diversity, the number of creature types. So this is basically the size of the encyclopedia. Number of creatures that you can detect and the age of tracks, so creatures that last for long. And I create penalties that are reflecting if the episode basically ends, if there's no creature at all, if everything is black, everything is white, then something is wrong. I just end the episode, put the reward down. And so the set of actions that we have are the S rules and the B rules, which are set, if you remember well, the notation for this S rule is like the number of neighbors that are in order to update the thing. I only do 3 digits one, because then it just gets a very large number of actions. So this is like 400 combinations maximum, where you have all the numbers between 1 to 8 and 123 and 87. And then I initialize the system with the game of life, so it would be 7S23B3 rule. So training details, maybe not so important, but I have a patch size of 10 by 10, which means my grid search is by 10 by 10. This can be, we can vary this a lot, and you're probably gonna have very different types of creatures depending on the size of your grid. And I update the rule every 5 frames, which is something you can also play with. I tried multiple things. You can do 10 frames, 20 frames, because updating the rule of the whole environment have a huge impact on how the environment will evolve. So I didn't know if I should give it a lot of control or a very small amount of control. Second thing, I trained in this one, I don't remember, 10 environments in parallel, which is very cool because that means you can train basically almost the same policy at the same time, but not exactly. So here are all the environments, like 6 environments in parallel at times 467. And you can see they all have a different state-ish, but kind of at a different, like you have the same positions of creatures, but there are different creatures. So that means they have maybe one rule that is changing between all these two over a certain amount of time. And that's, you can maybe compare and train better. Again, you need big computers to do this. So I don't think I really trained. I tried my best. So it looks a bit like this. And you can see that it looks like a lot of noise at the beginning because it's trying to stabilize it. At some point, it's gonna set a rule that destroys kind of everything, and it destroys way too much, so everything like is not very stable. And I tried a lot of things. Sometimes it's very epileptic. You have a lot of every time you change the rules, you have a lot of things happen. But I do think it's possible if you train for a longer amount of time and you also set the rewards correctly. So yeah, details doesn't really train with this type of parameters, and I mean you can try a lot, but you still do find some things, I think. Like you can extract an encyclopedia, you can extract the number of the type of rule, the policy of changing of rules that you have. And I do believe that if it works, you can also apply it to different systems, not just to the CA2 automaton, but you can basically take any type of system and try automatically to find what the rules are in order to simulate your biological system. So future work will probably be to try different type of policies because it's a great one, but maybe this is more simple ones that will work better for this type of system. And then make a better detector. I'm thinking of supervised learning with the convolutional network and optimize the reward function. I think my reward function is highly based on the number of detections. It's not well balanced. And then more training in general for different types of models. Et voilà. Questions? Yes.
You mentioned that you update the rules every 5 frames. I wasn't sure exactly what's being updated.
The rules. So your environments has.
So what's precisely the difference between the steps which you said were 20,000 and the update one?
So this yeah, it's kind of the same-ish. The 20,000 is just the number of total frames that you have. So you have maximum episodes of 250 frames that are next to each other for 20,000 frames. And then every 5 frame, your agent is able to modify your whole environment rules.
So you continue the simulation with another CA rule,
Yes,
but with the initial condition, which was from the last. Okay.
I don't reset the environment when I change the rules.
Is the 5 frames too short for this, so it seems weird that you would get into
I tried multiple things. I tried 500, 20, 10. It looks a bit the same all the time. You know.
I had a related question. So when you say that you initialize with the game of life,
yes,
does it mean that you just start with the rule which is the game of life, or also that your initial policy is just to keep the game of life for?
I tried that too,
okay.
But I don't know. I don't think my implementation was correct. Like I wanted to initialize policy, and I don't know how to do that.
Okay, that's fine. Because I was wondering, because the game of life, is it kind of the best in terms of score or not?
Probably not. That's what I'm. That was what I was thinking.
Yeah, yeah.
I guess that it was not the best.
But in your results that you get according to your
my reward
scoring, is it better than just the game of life?
Yes.
Okay, great.
Yeah, I can have better results, but sometimes it's just because you have very few frames where you find a lot of detections.
Right.
At one
yes.
time. Of course, it's really a matter of reward.
Right.
Yes.
At some point, when you first talked about the encyclopedia, you showed 4 little plots. And maybe it's because I'm a bit far away, but one of them. Sorry, I think it was slide 15.
Slide 15.
Yeah.
Well, like the one bottom left. So is it like the emergence of species? And I was wondering why it was like 0, 0, and suddenly, is it because it was like random initial conditions and then it started to open?
Good question. Do you think that at first it's random? Exactly, you have a random initial condition. So you have no creatures appearance for a certain amount of time,
Yeah.
and then at some points it stabilizes. Yes.
And then it's
Then it stabilizes as well. You have a maximum number of creatures of.
These curves are for the game of life.
Yes.
Did you try to plot these curves for other rules as well, or? Okay. I think you should try because I think kind of the shape of the curve would probably tell you something about the class of the rule, most likely. But yeah, it's very very cool. A question about the creatures. So the size of the creatures is predetermined, or it can be.
I don't. Yeah, exactly. It's the size of my grid, basically.
It's the size of the grid. Okay.
Yeah, but then you can also do the sum over
Right.
the number of pixels in your
Yes.
grid and do the size. Yeah.
Okay. So you said that this could be applied to other systems. So for continuous systems, the problem would be the definition of what is a creature because.
Yes.
Right.
Like here, I
Okay.
define it as a border
Yeah.
binary way.
Yes.
I'm sure
Okay.
there's you can probably do other types of detections for continuous systems. I mean, image classification is a thing.
And and a last question about the creatures as well. So, for example, if you have a glider, is it correct that like the four? I don't know what's the period of the glider again, but all the steps of the gliders are considered different creatures, right?
No, actually not. That's why I track them.
Ah, okay, I see.
That's why I track them. You have an example, I think, over here.
Yeah.
Here, it looks like you have multiple detections, but because there's an overlap, I use this track to know that it's actually the same creature.
Okay, well, that's very cool. Okay.
And then I will project so they also have the same data.
Right. Okay. And the colors in the pictures of the creatures that you show is like the period of the creature, or?
Basically, I take 3 frames for defining a creature. So the grid, I take it over 3 frames,
Yeah.
and I sum them up, so it creates a color because then you
Okay,
have
very
values
nice.
that are between 0 and 3.
Okay. Any other questions? Otherwise, yeah, it's time.
Just a remark, I feel like the automated detection of creatures is a pretty challenging problem in AI. So I'm intrigued by your solution and just taking that metric and exploring the space of rules and precisely looking whether the metric would be higher for other rules than game of life sounds like it's very interesting.
I think so too. I can share the GitHub if you want.